Hi everyone. In the last lecture, we started talking about how to use regression to test interactions between predictors. And all of the examples that we've looked at so far looked at interactions between one categorical predictor and one continuous predictor. So things like sex and signature size, or society and well-being score, or self-esteem and the type of praise that kids got. But what if we want to test for an interaction between two predictors, both of which are continuous variables? We can also do that using regression, and that's what this lecture is going to be about. How do we test for an interaction between two variables when both of those variables are continuous? So here's the first example we're going to walk through. It stands to reason that stress is related to a person's happiness, right? As stress increases, happiness or positive emotions tends to decrease. However, this study set out to examine whether engaging in pro-social behavior, meaning doing nice things for other people, moderates this relationship. So their prediction was that yes, there would be a relationship between stress and happiness, but that relationship would be weaker or maybe even non-existent for people who engage in a lot of pro-social behavior. In other words, their hypothesis was that doing nice things for other people actually protects us against the negative effects of stress. So maybe if we are very stressed, but we also are doing lots of nice things for other people, the stress won't have as much of an impact on our happiness. In more statistical language, what we're saying here is that the relationship between stress and happiness is moderated by pro-social behavior. It depends on how much pro-social behavior a person engages in. So here's what our regression equation is going to look like for this example. Our outcome variable, positive emotions, is being measured by the PANIS scale. So it's a continuous outcome. How happy is this person? Our first predictor is stress level, which is going to be measured continuously. And our second predictor is going to be the number of pro-social behaviors that this person has performed in the past, I think it was past week or month. Doesn't really matter. It's a continuous variable either way. And then we have the interaction between those two things. So just like we did in the previous lecture, we are going to build an interaction term between those two predictors. As with any time we have multiple predictors, alpha is going to be the predicted value of y when all of our x's equal 0. So in this case, our intercept would be the predicted level of happiness or positive emotions for someone who has 0 stress and engages in 0 pro-social behaviors. Because if all these things here are zeros, they're all just going to cancel out, leaving us just with alpha on this side. Now, here's what's going to make this week's lecture noticeably different from last week's. Last week, we tested for interactions between a categorical variable and a continuous variable. And whenever we found a significant interaction, what we did is we split the file by the categorical variable, and we ran separate simple regressions within each category. So one regression for men, one regression for women. Or in the other example, one regression for the US, one for Europe, one for China. And the reason we could do that is because one of our predictors was categorical. But now we don't have any categorical predictors. So we can't use split file to help us make sense of a significant interaction if we do in fact find one. So what are we going to do? How are we going to make sense of this interaction? One option, which is a bad option, and I'll explain why in just a second, is that we could take that continuous variable and make it categorical. So for example, we could take stress level and we could dichotomize it and take it from a continuous variable and somehow categorize people into being either low stress or high stress. And the way that people sometimes do that is by performing what's called a median split. So what they'll do is they'll take the median of their sample. Let's say the median stress score is 18, right? And anyone whose score is below 18 will be lumped all together into one group. And anyone whose score is above 18, they'll be lumped all together into one group. So that we end up with just two groups of people. One group that we would call low stress people, one group that we would call high stress people. And if we did this, we could then split file by stress level into low versus high and test for moderation that way. This is a bad idea. Very rarely do I recommend doing this. The reason is anytime you take a continuous variable and make it categorical, you're throwing away a lot of really valuable information, right? So imagine, for example, that this represents a person's stress score. So this person has a stress score of about 7. This person has a stress score of about 14. This person has a stress score of about 25, and so on. What we're doing is we're treating all of these people on this side of the median as if they're the same, and we're treating all these people as if they're the same. In other words, this person who has a stress score of 0 and this person who has a stress score of 15, they're being treated as if they're equal to each other, which we know they're not, right? They're quite different. And the bigger problem is that people who are just on either side of the median are being treated as if they're totally different. So this person with a score of 15 and this person with a score of 20 are being treated as if they're completely different, whereas a person with a score of 15 is being treated as the same as a person with a score of 0. So it's a very kind of weird approach to do this. The other potential problem we run into is that we might lose some data. Because if anyone's score falls directly on the median, we can't keep them, right? We can't really consider them either high or low because they're not above or below the median. So we might have to even throw those people out. So for a lot of reasons, it's not a good idea to do this median split thing. It's almost never a good idea to take a continuous variable and make it categorical because you're necessarily throwing away information. So if we can't use a categorical variable here, what does that leave us with? And that's what the main focus of this lecture is going to be, is on a procedure called a simple slopes analysis. The way that a simple slopes analysis works is we don't actually change the data in any way. We don't actually throw out any of the data, but what we're going to do is we're going to change how we weight different people. So we're going to weight the lower scores more heavily and see how that changes our relationship. Then we're going to weight the higher scores more heavily and see how that changes our relationship. And by low and high, the standards usually for low and high are 1 standard deviation below the mean is a low score, 1 standard deviation above the mean is a high score. And we'll talk in a minute about what exactly that means from a mathematical perspective. But what we're ultimately going to end up with are 3 different things that we need to report. What does the relationship look like when we focus on people who are low? What does the relationship look like when we focus on people who are average? And what does it look like when we focus on people who are high? So for example, let's say we ran a simple slopes analysis and we found something that looks like this, right? For people with high scores on our moderator variable, the line is flat. So for those people, it doesn't look like there's much of a relationship. But for people who have low scores on one of our moderator variables, or I'm sorry, on our moderator variable, we only have one, the red line has a pretty noticeable slope to it. So it looks like there is a relationship here for the people who score low in our moderator variable. The overall trend shows that as the moderator gets higher, the relationship gets weaker, right? So if the moderator is low, we have a relationship. If the moderator is average, we have a fairly flat line. If the moderator is high, we have a very flat line. If this isn't making a whole lot of sense yet in the abstract, don't worry about it. We're going to make it a lot more concrete very soon and think about how this actually functions. So here's what the example looks like. We're going to use the data file stress.sav. For each participant in this study, we have 3 scores. We have their stress score, we have the number of prosocial behaviors they have performed, and we have our outcome, which is positive emotions. So here are the steps that we're going to have to follow to test for an interaction between stress and prosocial behavior, our two predictors. And they're going to look very similar to the steps that we did last week. In fact, they're even a little simpler, I think, than the steps that we did last time. So first, because both of our predictors are continuous, we now need to mean center both of them. So we're going to mean center stress and we're going to mean center prosocial behavior. Then to calculate our interaction term, all we're going to do is we're going to take those two mean-centered variables and multiply them by each other. And then just like we did last time, we're going to run a regression with both predictors and the interaction. Now, last week we did this in a hierarchical way. This time we're just going to cut to the chase and we're just going to throw all three variables in the regression at the same time, and we're going to focus on the interaction term. And then if the interaction is significant, spoiler alert, it's going to be, we're going to perform a simple slopes analysis, and we'll see how exactly to do that, and we'll talk a little bit more about how exactly it works. But before we get to that, let's walk through these first three steps to refresh our memory. So first we need to mean center both predictors, which means we need to find the mean for each of those things. So here's the mean for prosocial behavior. Here's the mean for stress level. So using syntax, we are going to compute mean-centered stress by subtracting the mean stress score from each person's stress score. And we're going to compute mean-centered prosocial behavior by subtracting the mean for prosocial behavior from each person's score. Then right below that, in line 3 here, I compute the interaction term by taking the two mean-centered variables that we just created and multiplying them by each other. So we're going to end up with a data file with 3 new variables in it: mean-centered stress, mean-centered prosocial behavior, and then the interaction between those two things, which is just those two things multiplied by each other. We will go in to linear regression. Again, we're not going to bother doing this hierarchically this time. We're just going to put in all 3 of those variables we just created. We're just going to put all of them in block 1, mean-centered stress, mean-centered prosocial behavior, and the interaction term. And our outcome variable is positive emotions. When we run the regression, we're going to jump right down to the coefficients table, and we're going to look at the interaction, and here we see that the interaction is indeed significant. P equals 0.001. There is an interaction between stress and prosocial behavior in terms of predicting positive emotions. Okay, so we know from this, all we know so far is that the relationship between stress and happiness depends on prosocial behavior. We don't yet know what exactly that means, but we know that somehow all 3 of these variables are related to each other. If we want to make sense of it, we're going to do a simple slopes analysis. Now, let me explain to you how exactly this simple slopes analysis works. A simple slopes analysis works in the same way that a seesaw does. So if you've ever ridden a seesaw on a playground, you kind of understand how simple slopes works. On a seesaw, the fulcrum, this thing in the middle, is directly in the middle, right? It has to be right in the middle of the seesaw so that it's balanced on either side. Think of the length of the seesaw as being like the range of scores in our sample. So down here you've got the lowest score in the sample, up here you've got the highest score in the sample, so in the middle you've got the average, right? So on a seesaw, on a normal seesaw, the fulcrum sits right in the middle at the average between the lowest scores and the highest scores. We just mean-centered our predictors. So right now, a score of 0 means that you're right in the middle. It means that you're right at the fulcrum, right in the middle of the seesaw. So average scores are the ones that we're really fixated on when we're mean-centered. And if you've been on a seesaw, you know that if you have 2 people sitting on each side that weigh the same amount, the seesaw will be perfectly balanced, right? As it is right here. What a simple slopes analysis is going to do from a mathematical standpoint is instead of actually manipulating the data or throwing out any of the data, we are just going to change how the scores are weighted. And the way we're going to do that is by moving the fulcrum on the seesaw. So if you move the fulcrum to one side, what you end up with is one arm of the seesaw is now shorter than the other one. And again, if you're familiar with, physics and how seesaws work, you know that the longer arm means these scores on this side are going to be weighted more heavily. So instead of mean centering our variable, what we're actually going to do is we're going to center it at one standard deviation below the mean. We're intentionally going to center it off center, so to speak. And what that does is it keeps all of the scores, but it's now going to weight the high scores more heavily than it weights the low scores. So if you had a score of 0 in this scenario, what that would mean is that your score is exactly one standard deviation below the mean. Then we're going to do the same thing, but move the fulcrum the other way. So instead of centering our seesaw at one standard deviation below the mean, we're going to center our seesaw one standard deviation above the mean, and it's just going to do the opposite. So when we do this, the low scores are now being given more weight, and the high scores are being given less weight. So this is kind of similar. You can think of this as being kind of similar to splitting the file, right? If we do this, and we weight the high scores more heavily than we weight the low scores, what this is going to tell us is, what does this relationship look like when we prioritize people who have a high score on whatever our moderator is? So, for example, if we're testing the relationship between stress and happiness, what does this relationship look like for people who are high in prosocial behavior? Then we're going to do the same thing for people who are low in prosocial behavior. If we weight their scores more heavily, what does the relationship between stress and happiness look like for those people? Again, this is all very abstract, I know, and it's going to get a lot more concrete very soon when we see how to do this in SPSS. It sounds very complicated, but it actually turns out to be very, very simple. No pun intended. Now, normally at this point in the semester, I would walk you through how to manually do a simple slopes analysis in SPSS. It is a pain in the ass to do. It requires a lot of syntax, a lot of steps, creating a lot of new variables. We are going to skip that. So I'm going to skip through all of these slides really quick. If you are curious to learn how to do this, you are more than welcome to go through those slides and learn how to do it the long way. The reason I'm skipping through all of this is because there is a much easier way that we can do this in SPSS. There is a shortcut that we can build into SPSS that will allow us to do simple slopes analyses very quickly. So there's really no reason why you would do it the long way anymore, because we can do it the short way. This guy is a statistician named Andrew Hayes. You might remember talking about him a little bit in the fall semester, but he's going to come up again quite a bit for the rest of this semester as well, because he invented this add-on program to SPSS that's called Process. And this add-on to SPSS allows us to do things that used to take a really long time. It allows us to do them really, really quickly in SPSS. So we're going to learn this semester 3 or 4 things that Process can do. But there's a whole lot of stuff that Process can do that we're not going to have time to get to this semester. There's literally, I think, 90 or so different things that Process can do. We're going to only focus on the 2 or 3 that are most important for us, that I think you're most likely to use. But just so you know, if you Google either Andrew Hayes' name or you Google the words process macro, You'll get a website with a whole bunch of information about the many things that this program can do. So he is a real lifesaver for creating this program that is not only really helpful, but also free. So we can all download it and install it and use it, and it'll make our lives much easier than they would have been, 10 years ago or so. So the first thing we need to do is we need to install this program. Now, I trust that you all were able to get the free trial of SPSS installed on your personal computers. If you haven't done that yet, now would be a good time to pause the lecture and do that. Thankfully, IBM has made that free trial free until June 15th, which will be much longer than you'll actually need it for. But that way, should you need it for your first year project or your thesis, that'll also be nice because you can just use it from home. Once you have SPSS installed on your laptop, then you can go ahead and install Process, which I'll walk you through how to do right now. Okay, so to install the Process macro, you're going to go to processmacro.org. The website should look something like this, and you're looking for the download button at the top, which will take you to the relevant version of Process for you to download. I can't remember off the top of my head if it's different for Mac versus Windows, but either way, the process of installing it should be exactly the same. You'll click the download button, and it will give you a zip file to download called processv34.zip. Save that file somewhere. I say here save it on the desktop. You don't have to save it on the desktop. Just make sure you know where you saved it because you're going to need to find it in just a few minutes. Once the download is complete, you may or may not need to unzip the folder. From past experience, sometimes the folder will unzip on its own, sometimes it won't. So if you find it and it's still a zip file, you're going to want to right click on that and click extract all, which will unzip it for you, and it will turn it from a zip file into just a regular old folder. Once you've done that, go into SPSS, open SPSS, and here's where you're going to go. You're going to go to Extensions, Utilities, Install Custom Dialog. Now, when you click Install Custom Dialog, a little box is going to pop up. That's where you're going to have to find where you just downloaded that process file and saved it to. So you got to navigate to that folder wherever you saved it. You're going to find a file in that folder called process.spd. And you'll double click on it to open it just like you would open any other file. Once you do that, SPSS will automatically know that you want to install this program, and it will install it for you. Okay? So again, install custom dialog, navigate to wherever you downloaded the program, find this file in that folder and just open it. And then once SPSS does its thing, which might take a minute or two, in the Analyze Regression menu, you'll see something in there that wasn't there before, right? We will now have an option called Process version 3.4 in that regression menu that we've been using for the last few weeks. So this is what we're going to use to do simple slopes analyses in SPSS. If we open Process, this is what the window looks like. And again, there's a whole bunch of different things that Process can do. We're just going to use it right now to do a simple slopes analysis. So getting back into our example, what we know so far is that the relationship between stress level and positive emotions somehow depends on prosocial behavior. But we don't know exactly what that interaction looks like yet. So now we're going to run the simple slopes analysis in Process. Our predictor is going to be stress level. Our outcome, y, is going to be positive emotions. And our moderator, which Process calls w, is going to be prosocial behavior. So we move those three variables to the respective boxes that they need to go in. Under model number, I think model 1 is selected by default, but if it isn't, make sure that model 1 is the one that you have selected. I said a few minutes ago that process can do about 90 different things. This is one of those 90 things, and if you click this drop-down menu, you'll see a list of all the things that process can do. If you're curious to learn more about these things, there's a manual available online that goes through every single different analysis that process can do. This is a diagram of what model 1 looks like. So we have a relationship between x and y that is moderated by some other variable. So in this case, we have a relationship between stress and positive emotions that is moderated by, in other words, it depends on prosocial behavior. So our regression is going to have 3 predictors. We're going to have stress as a predictor, we're going to have prosocial behavior as a predictor, and we're going to have the interaction between those things as a predictor. So for every single different type of analysis that process can run, the manual online has a conceptual diagram as well as a statistical diagram that shows you what's actually happening when you run that model. Okay, before we run the analysis, we are going to click on the options button and we're going to get a window that looks like this. There are a few things in here that we want to change. So the first thing we're going to do is we are going to ask process to mean center our variables for us. So when we did this previously, we used syntax to mean center our variables manually. We don't have to do that anymore. Process will do it for us. If we check this box right here, only continuous variables are the ones that we want to mean center, so we don't even have to worry about using syntax anymore. The other thing we need to do is tell process what do we want if we find a significant interaction. So first, we tell it we only want to examine an interaction if the p-value for the interaction is less than 0.05. That certainly makes sense, right? We only want to examine an interaction if it's significant. And then remember, in a simple slopes analysis, we're going to look at low, average, and high levels of our moderator. This is a menu that gives us 2 different ways of defining what low, average, and high means. We're going to choose the second one. So negative 1 standard deviation, 1 standard deviation below the mean is going to be considered a low score. The mean is, of course, our average. And then 1 standard deviation above the mean is going to be considered our high score. So make sure you, after you put the variables where they need to go and you select model number 1, make sure you go into that options menu and fix these options before you actually run the analysis. I will forewarn you that the output for process looks very different than the output that we're used to seeing from SPSS. When you run the analysis, you're going to get output that looks like this here. So it's not tables and nicely formatted things. It's just a bunch of text that we have to make sense of. So here's the output for this particular problem. At the top, we have the original regression, right? So we have stress, prosocial behavior, and their interaction as predictors of positive emotions. We're used to seeing this as the coefficients table, right? In previous examples where we've done this, we've gotten a table called coefficients. This is basically the equivalent of that table. So we have a row for our constant, we have a row for prosocial behavior, we have a row for stress, and we have a row for the interaction. The bottom part of the table, which we'll get to in a second, shows the results of the simple slopes analysis that helps us make sense of our interaction. So first, let's slowly walk through this output so that we can understand what's what here. Even though it looks very different, it gives us all the same information that we're accustomed to getting. It just is formatted in a slightly different way. So the first box up here gives us the model summary. This is the model with all of the predictors in it: prosocial, stress, and the interaction. R squared is about 32%, and we see that the overall model with all three predictors is significant. In other words, having all three of these predictors is significantly better than having none of these predictors. That doesn't really tell us a whole lot, but if we wanted to know that for some reason, we could see that here. This is the information that we care about more. For each of the three predictors, we get a t-test telling us whether that predictor was or wasn't significant. In this case, all three predictors were significant. Prosocial behavior was a significant predictor of happiness, stress was a significant predictor of happiness, and most importantly, the interaction was a significant predictor of happiness. So we need to make sense of that interaction. If we had done this hierarchically, and we had entered prosocial behavior and stress in block 1, and then added the interaction in block 2, we would have gotten that F-change test that we're accustomed to seeing, that compares block 2 against block 1, to tell us whether adding the interaction term made the model better. What I have here highlighted in purple is that same test, so we don't even have to separately ask for it. Process gives it to us automatically. So what this tells us is that adding the interaction term did in fact make the model better. The model was better with the interaction than it was without. Here we see adding the interaction increased R squared by about 10.5%, and that was a significant improvement. It's no coincidence that this p-value here is the same as this p-value here, because these are just two different ways of testing whether the interaction is significant. So either of those is an equally good way to tell if the interaction is significant. In this case, it is. I'm just going to jump back for a second. We're taking the slopes. These numbers right here, negative 3.17, negative 1.37, and 0.41, those are the slopes of the regression line for people who are low, average, and high in prosocial behavior respectively. So all SPSS is doing is taking those three slopes and graphing them in a way that's easy for us to see. Negative 3 point whatever, negative 1 point whatever, and positive 0.4. Oh, and there they are. So pulling all of this together, how would we write up our results? First, we're just going to simply explain what we did, and we're going to cut right to the chase and talk about the significant interaction. So we did a regression. We used stress, prosocial behavior, and their interaction as predictors of positive emotions, and we found that the interaction was significant. To make sense of the interaction, we did a simple slopes analysis, and what we found is that the relationship between stress and positive emotions was significant when prosocial behavior was either low or average, but it wasn't significant when prosocial behavior was high. In other words, the more prosocial behavior you did, the weaker that relationship got. If you did very little prosocial behavior, it was a strong relationship. If you did an average amount, it was a negative, significant, but weaker relationship. And if you did a lot of prosocial behavior, there was no relationship. So it does appear in this case that doing nice things for other people protects us against the damaging effects of stress. Here's the article that this example is based on. They actually looked not only at positive emotions, but also negative emotions. So they did this twice. And here are the graphs of their simple slopes analyses. So for positive emotions, which is what we just looked at, people who were low in prosocial behavior showed a negative relationship between stress and happiness. But for people who were high in prosocial behavior, the solid line was pretty flat, right? For those people, stress and happiness were not related to each other. For negative affect, they found a similar pattern, But engaging in pro-social behavior didn't completely make the relationship go away. It did make it weaker, though, right? You can clearly see that the slope of the solid line is less than the slope of the dotted line. So it looks like, in terms of the effects of stress, engaging in pro-social behavior is not only protecting us from not experiencing positive emotions, but it's also protecting us from experiencing negative emotions. Whoops, sorry. Don't forget to make sure that model number 1 is selected. So at this point, if you would like to pause and try to do this on your own so that you can practice, you can write up your own answer, and then we'll walk through it together and you can check your own work and check to make sure that your interpretation was correct. So if you want to practice this, go ahead and pause now. Okay, so let's see how we did with this problem. Here is what your output would look like. Let's walk through this. Neither of the main effects was significant. So surface acting was not a significant predictor of exhaustion, and emotional intelligence was not a significant predictor of exhaustion. However, we do have a significant interaction, and we could see that either from the t-test up here, or probably better, from the F-change test down here, telling us that if we had built this model hierarchically, the model with the interaction is better than the model without it. So we know that the effect of surface acting on emotional exhaustion depends on a person's level of emotional intelligence. We don't know how yet. To make sense of that, we need to go down and look at the simple slopes analysis. We have a row for people who are low in emotional intelligence, a row for people who are average in emotional intelligence, and a row for people who are high in emotional intelligence. So for people who are low in emotional IQ, there was a significant positive relationship, that higher levels of surface acting produced higher levels of exhaustion. However, for people who were either average or high in emotional intelligence, that relationship was not significant. So the interpretation here would be that engaging in surface acting is very exhausting, but only for people who are low in emotional intelligence. For people with an average or high amount of emotional intelligence, surface acting did not predict exhaustion. Here is what that looks like in a graph. Again, I'll add the lines just so you can easily see the dots here. The blue line is people who are low in emotional IQ. The green line is people who are average. The brown line is people of high emotional intelligence. And what you see here is that the blue line clearly has the steepest slope, right? For people who are low in emotional intelligence, there is clearly a positive relationship between surface acting and exhaustion. The more they have to surface act, the more exhausted they get. But for the other two groups, the lines are relatively flat, which is consistent with the fact that they were not significant on the previous slide. So for those people, surface acting was not predictive of exhaustion. So here's how we'd write up these results. First, we're going to just say what we did, and we're going to talk about the interaction. So our regression included surface acting, emotional intelligence, and the interaction between those two things as predictors of emotional exhaustion, and we did find a significant interaction in that F-change test in the output. So we then went and did a simple slopes analysis, and we found that surface acting predicted emotional exhaustion, but only for people who were low in emotional intelligence, not for people who were average or high in emotional intelligence. So for these tests, as always, I'll be very clear about what exactly to report. What I've reported here is the standardized beta, T and P, for each of the three levels of the simple slopes analysis: low, average, and high. So, ironically, as our analyses are getting more complicated, they actually have fewer numbers in them, right? Look how few numbers are actually in this write-up here. But we're describing a relationship that's actually pretty complicated. You may want to pause here and just compare the results that you got against the results that I got, and make sure that you understand where all these numbers are coming from and how we're making sense of them. So if you want to do that, go ahead and do that. Otherwise, we're going to move on and look at the actual results of this study. So they presented their results in a table rather than in a graph. In step 1, they controlled for negative affect as a potentially confounding variable. In step 2, they added the two predictors, surface acting and emotional intelligence. And then in step 3, they added the interaction. And as you can see here, the interaction was significant. So then they went ahead and broke it down. And in their own words, they did a simple slopes analysis for people who scored 1 standard deviation either below or above the mean on emotional intelligence. And ultimately what they found is that surface acting increased emotional exhaustion, but only for people who were low in emotional intelligence. So it looks like having high emotional intelligence is actually a protective factor in this case against the exhausting effects of having to be fake nice to people. One more example to walk through. Again, if you want to pause and do this one on your own, you're certainly welcome to do that for practice, and I very much encourage it as a good way to test your own understanding of this stuff. Obviously, there's a lot of research that has looked at the relationship between playing violent video games and acting aggressively. This probably looks familiar to some of you. This is the Bobo doll from Albert Bandura's classic studies of observational learning, where kids saw an adult, aggress against the Bobo doll, and then they started doing it themselves. So it's somewhat controversial whether there is a relationship between playing violent video games and acting in a more aggressive way. The study that I'm going to tell you about now tested whether the relationship between violent video games and aggression is actually stronger for some people than others. To be exact, they looked at personality as a potential moderator of this relationship. So maybe, in other words, maybe these variables are related for people with certain personality traits. So our predictor variable is going to be the amount of time that a person spends playing violent video games, and our outcome variable is a measure of aggression. Our moderator is going to be a personality trait called callous unemotional traits. I didn't know what that was, so I had to look it up. Callous unemotional traits are things such as lack of guilt, lack of empathy, and callous use of others for one's own gain. So the hypothesis here is that there may be a relationship between playing violent video games and acting aggressively, but maybe that relationship only exists for people who are score higher in these callous unemotional personality traits. Here is the data file. So you've got, for each person, you have an aggression score that tells us how aggressive they behave. You have a score that tells us how frequently they play video games, and you have a score for their callous, unemotional personality traits. So first, build the model in process. Tell me if the interaction term is significant. Second, look at the simple slopes analysis. So does video game use predict aggression for people who are low in these traits, for people who are average in these traits, for people who are high in these traits? And produce a graph, get the syntax to produce a graph that displays the results of the simple slopes analysis. So again, this is where you would want to pause if you want to go ahead and practice, so go ahead and pause now. All right, let's walk through this one. Here is how we would set this up. Video games is our X variable, aggression is our Y variable, callous unemotional traits is our W variable, our moderator. In the options menu, we're going to ask for syntax to create a graph. we're going to ask process to mean center those continuous predictors for us, and we're going to have the interaction tested at plus or minus 1 standard deviation for the simple slopes analysis. Here's what the output looks like. You probably learned by now we can just jump right to the interaction, but let's resist the temptation to do that. Violent video games do predict aggression. Callous unemotional traits do predict aggression, but these effects were qualified by a significant interaction. So it looks like the relationship between video game use and aggression does in fact depend on a person's level of callous unemotional traits. Here we have a row for people who scored low in those traits. We also have a row for people who were average and high in those traits. But we see that for people who were low in callous unemotional traits, this relationship was not significant. So playing violent video games was not related to aggression if a person is low in this particular personality trait. However, if they were average or high in those traits, it does predict aggression. In other words, violent video games do predict aggression, but only for people who are average or high in callous unemotional traits. That's where the interaction is coming from. So again, here's how we'd write up our results for this. I just really cut to the chase here. The relationship between violent video game use and aggression was moderated by, remember that moderation and interaction are synonyms, was moderated by callous unemotional traits. Here's the results of that F-change test that we saw previously. And then here's the results of our simple slopes analysis, and there's your graph. So for people who are low in callous unemotional traits, there was no relationship. Look how flat that blue line is. But for people who have an average or high level of callous unemotional traits, video game use did predict aggression. In other words, what we're seeing here, the overall trend, is that as callous emotional traits increase, this relationship gets stronger, right? It goes from non-significant to weak to somewhat stronger.